Applications of Integration, Lesson 6, the Exponential Distribution. In this lesson, we're going to apply integration techniques to solve practical probability density function problems. In particular, the focus of this course is using the exponential distribution in this form to model data such as wait times and determine things such as the mean, median, and standard deviation of those life-related problems. We can choose many functions that satisfy the conditions to be a probability density function. They are: f is non-negative, that is fx is greater than or equal to 0 for all x values that are elements of the real number system. The area under the graph of the function is equal to 1, as given by the definite integral. The exponential distribution satisfies the conditions for a probability density function, also known as a PDF for short. The exponential distribution with parameter lambda has the probability density function given by fx equals lambda e to the negative lambda x for all values where x is greater than or equal to 0 and 0 elsewhere. It is a simple distribution defined for all positive values of x. However, since it is a parameter or contains the parameter lambda, it is really a family of distributions, with each distribution determined by the value of lambda. For instance, if I was to apply 0.8 as being lambda, this is what it looks like. Fx, gx, and hx. You can see they're all exponential curves that are diminishing in value. And the area under each of those curves equals 1. So they're a family of curves that are considered an exponential probability density function. Example 14. The time x minutes that a shop assistant waits before the next customer arrives is known to be exponentially distributed with probability density function given by the following. Calculate the probability that she'll wait between 2 to 4 minutes for the next customer to arrive. Setting up a probability statement, the probability that we wait between 2 and 4 minutes can then be approximated or determined by the exponential distribution, which is given by the definite integral between 2 and 4 of fx. Integrating this is quite simple. When you're integrating e to the kx, the derivative of that kx is k. If we divide by k, you're really going to have 0.75 divided by negative 0.75, which is negative 1. Our terminals are 2 and 4. Substituting in our upper and lower, the probability that we wait between 2 and 4 minutes is 0.1733, which is approximately 17%. In example 14, we're going to look at question B. That is, calculate the probability that she will wait more than 7 minutes for the next customer to arrive. On the right here, Symbolab has been used to verify or check the answer later on. But as you note, our lower boundary is 7 and our upper boundary is positive infinity. The answer is about 0.5%. What's interesting to note, when you actually compute the boundaries, you'll have a 0 here. So let's have a look. The probability that x is greater than 7 is the definite integral from 7 to the upper boundary of infinity. First step is to find the antiderivative or integrate, and that is when we divide by negative 0.75, we're going to have negative 1 e to the negative 0.75x. Now it's kind of like a limit question where our lower boundary is 7 and the upper boundary k is where k approaches infinity. If I was to sub in 7 to negative e to the negative 0.75x, that's fine. That gives a nice number. But if you actually sub in something that approaches infinity, what you're talking about is very, very large numbers. Now, if you use index laws, it's actually negative 1 over e to the 0.75x, which means you're dividing by an extremely large number as k gets closer to a positive infinity. Hence, that limit approaches 0. So here, I'm realistically just subbing in the lower one, which is 7, and I'm going to have a take, which becomes a plus. So e to the negative 5.25 is approximately that 0.5%. It's not as common to work out greater than x being greater than a number. More likely to get asked x being less than 7 minutes. Wait time for an event to occur and the average number of events in the time period is lambda, the parameter. The average wait time is given by e, x equals 1 over lambda, and interestingly, it's also equal to the standard deviation, which is 1 over lambda. We're going to use those formulas now to answer a few more questions to finish off our topics in PDFs. So example 14. Time X minutes that a shop assistant waits before the next customer arrives is known to be exponentially distributed. The probability density function given by the following. So it's a continuation of our previous example, but now I've got question C. Determine the mean standard deviation for the wait time. Here, expected value or mean is 1 over lambda, where our value for that is 0.75. So 1 over 0.75, which is 3/4, means that our average or mean wait time is 4/3 minutes. Standard deviation is the same value again, which is 1 over 3/4, which is 4/3 minutes. Standard deviation is 4 over 3 minutes. The time taken, t minutes, that it takes a librarian to locate a book is exponentially distributed with the mean of 5 minutes. In this case, we don't actually have the probability density function. We're going to have to figure that one out ourselves. So the first step is to determine the PDF. Step 1 is to determine the parameter lambda. Now, applying our rule for mean, which is mean equals 1 over lambda, if we know the mean is 5, we can solve for lambda, which the parameter means is 1/5. Now that we have that, we actually can use that and develop a probability density function. So step 2 is to write the exponential probability density function. That is the probability that x is less than 1 minute is given by the definite integral where our values for lambda are 1/5 or 0.2. Our lower and upper is 0 and 1. If we now anti-differentiate by dividing 0.2 by negative 0.2, we get negative 1 e to the negative 0.2x. We substitute in our lower and upper boundaries. The probability that we're going to wait less than 1 minute is 0.183, or 1813, which is about 18.13%. Note, the exponential probability density function is a continuous random variable. Hence, the probability that x is less than 12 is also equal to the probability that x is less than or equal to 12. Is the fact to know about the continuous random variables. Note that is different for discrete random variables. The median of a PDF is the number m, given that m to some number of positive infinity of fx dx is equal to half. So it's like half your area is below that value, which is the median. Example 15b. The waiting time x for the ticket purchase at a cinema is modelled by the exponential probability density function given by fx. Calculate the median wait time. So solution. Write a valid probability statement. That is, the probability that x is less than some value m has to equal 0.5. So now develop a suitable definite integral equation, which is our lower boundary is 0, our upper boundary is some value m. Our integrand is 0.2 e to the negative 0.2x, and the area, well, when we evaluate this, has to equal 0.5. It's half the area underneath the curve. Step 3, anti-differentiate and solve. So as a definite integral, we need to solve for the upper boundary m. The first step is to integrate or anti-differentiate, which is negative e to the negative x on a. Now our lower boundary is 0 and our upper boundary is m, and this is all going to equal 0.5. So let's set that up. In terms of our lower boundary, subbing in a 0, and our upper boundary, which is an m. Now e to the 0 is 1, so you're going to have minus negative 1, which is plus. So we have a negative e to the negative m on 8 plus 1 equals 0.5. Let's take 1 from both sides. Next step, we're going to have multiply both sides by negative 1 or divide both sides by negative 1. And we have a statement e to the negative m on 8 equals 0.5. Now you're going to use your log laws. So we're going to take the natural log of both sides. So ln of 1/2 equals negative m over 8. The inverse operation is then to multiply both sides by 8, then divide by negative 1. So m equals negative 8 ln of 1/2, which is 5.55 minutes. So the median wait time is 5.55 minutes. To test your understanding, we've got a question here about Uber wait times. The expected time for an Uber is given by the function ft. Calculate the probability that you'll wait between 1 and 2 minutes. So have a go at the completing this question and check that your answer is approximately 11.99%.